Okay, so here we have differential equations and separation of variables, and much like Ronseal-wood stain, separation of variables does exactly what it says on the tin. So here's the theory. We've got a derivative equal to a product of functions in x and in y. And just like it sounds, we are going to separate out those variables. This is dy by dx, and because the numerator term is in y, I want the variables that are in y on the left hand side. So I'm just going to divide both sides by g of y. So I've got g of y dy by dx is equal to f of x. Now I can integrate both sides with respect to x, so I integrate here with respect to x, integrate here with respect to x, and I'll end up with my solution, which will be the integral of 1 over y dy being equal to the integral of f of x with respect to x. So that's the theory. We just separate out our variables and then we integrate. Okay, so let's look at that in practice. So here's our first example. Now in this case there are no variables to separate, so I can just go straight into integration. If I've got dy by dx is equal to 8, I can integrate both sides straight away. Integrate this with respect to x, integrate this with respect to x, and I've got the integral of dy is equal to the integral of 8 dx. Now really this is the integral of 1 dy. If I integrate 1 with respect to y, I get y. If I integrate 8 with respect to x, I get 8x. And of course I must not forget my constant c. Now a good question would be, why don't we have a constant of integration on this side as well? And the answer to that would be that if I added a constant of integration here and here, I could simply subtract this constant of integration to the right hand side and I would be left with essentially what we've got here. But long and the short of it is, keep your constant of integration just on one side. I prefer the right. Here's our second example. Okay, so this time we do need to separate out our variables. Again, we've got dy by dx. dy is first, so I want to bring my y's to the left hand side and end up with y dy by dx is equal to x squared. From here I can integrate, so I integrate this with respect to x, and I integrate this with respect to x. This becomes the integral of y dy, which is equal to the integral of x squared dx. The integral of y with respect to y is a half of y squared. The integral of x squared with respect to x is 1/3 of x cubed. And again, mustn't forget my plus c. Now I could choose to rearrange this to give my expression in terms of y, but I'm just going to choose to leave it as it is. Example number 4. Okay, so this time I'm going to divide through by y squared. Is going to be equal to x. And again, in exactly the same way, integrate with respect to x, and I find out the integral of 1 over y squared dy is equal to the integral of x dx. Now I prefer to have this written all on one line in single powers, so and from here add 1 to the indice and divide by the new indice, and I get minus y to the power of minus 1 is equal to 1/2 of x squared. Again, don't forget your constant of integration. Okay, again we can look at rearranging this. So for instance I can say that this is 1 over y and this is 1/2 of x squared plus c, and I could manipulate my y's and divide through and so on and so forth, but I'm just going to leave it at that. Okay, next question. Again, separating out my variables because I've got a product of two functions, one in x and one in y, so I separate them out. I've got 1 over y dy by dx is equal to sine of x. Integrate on both sides with respect to x, and I've got that the integral of 1 over y dy is equal to the integral of sine of x dx. Now, the integral of 1 over y is of course log of y, which is equal to the integral of sine, which becomes minus cosine of x. Again, don't forget our constant of integration. I could choose to here raise everything to the power of e. So on the left hand side, if I raise that to the power of e, I would get y, and on the right hand side I'd end up with e to the minus cosine x plus c. Now, remembering my rules for indices, this is y is equal to e to the minus cosine x times by e to the c. Now, when we raise e to a constant, it is still constant, and usually we refer to this as a. So my final answer is going to be y equals a e to the minus cosine x. Okay, final question is now moving on to a sort of boundary value problem where I've got initial conditions. The first thing I want to do is to find a general solution. Okay, so far everything we've done is to find a general solution, because if, for example, we switch back to example 5, it was general because we didn't know what this value of a was. If we were given values for x and y, we would be able to find a, in which case we would have a particular solution. So let's start off with the first part of this question, which is to find the general solution for this differential equation. Again, if we look at this, we realise now that we're dealing with different variables. This one is dx by dt. Because dx is my lead term, I would need to make sure that my x's are on the left hand side and that my t's are on the right. So I'm going to rewrite this as 1 over the square root of x dx by dt is equal to 1. Now I write this in single powers of x, all on one line, so this becomes x to the power of minus a half dx by dt is equal to 1. This time I'm integrating with respect to t. And if I do that, I end up with the integral of x to the power of minus a half dx is equal to the integral of 1 dt. And following this one through, this becomes 2x to the power of a half, and this becomes t. Again, don't forget my constant of integration. For the second part of the question, where I'm finding the particular solution, okay, that's when x is 0, that t is 0. So if I substitute those values in, x equals 0, t equals 0, I've got 2 lots of the square root of 0 is equal to 0 plus my constant of integration, which tells me that 2 must be equal to, beg your pardon, awful mistake to make. 2 lots of 0 obviously is still 0, which tells me that c must be 0. So my final solution for this particular integral would be 2x to the power of a half is equal to t. That's it. Thanks for watching. Next video in this series will be on exact equations.